Right now, as you sit here watching this, there are 5 human-made objects leaving our solar system. 5 tiny machines, built by human hands, drifting deeper and deeper into the darkness between the stars. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, New Horizons. They are moving away from Earth at tens of thousands of kilometers per hour, and they will never stop. They will never slow down, they will never turn around, and they will never, ever come back. Not because we forgot to plan for their return, not because we ran out of money or lost interest, but because we simply cannot bring them back. The laws of physics will not allow it. And here is the part that should send a chill down your spine. The same laws that prevent us from retrieving those 5 machines may also prevent any human being who travels deep enough into space from ever returning to Earth. This is not science fiction. This is not speculation. This is the cold, hard, mathematically provable reality of deep space travel. And today, we're going to explore every single angle of it. Let me start with some numbers that will put things in perspective. Voyager 1, launched in 1977, is currently approximately 173 astronomical units from Earth. 1 astronomical unit is the distance between Earth and the Sun, about 150 million kilometers. So, Voyager 1 is roughly 25.8 billion kilometers away from you right now. If you sent a radio signal to Voyager 1 at the speed of light, the fastest speed anything can travel in this universe, that signal would take over 22 hours to get there, and then another 22 hours for a reply to come back. A simple question and answer takes nearly 2 full days. Now, consider this. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. That is approximately 40 trillion kilometers. Voyager 1, the farthest human-made object in existence, has been traveling for almost 49 years and has covered roughly 25.8 billion kilometers. It has not even left the gravitational influence of our Sun. At its current speed of about 17 kilometers per second, Voyager 1 would take approximately 73,000 years to reach Proxima Centauri. 73,000 years. The entire recorded history of human civilization is only about 5,000 years old, and that is just the trip there. Coming back would double that number. 146,000 years for a round trip to the nearest star. Let that sink in. Now, let me give you another number. In December 2024, NASA's Parker Solar Probe set the all-time speed record for any human-made object. It reached 692,000 kilometers per hour, or about 192 kilometers per second. That is fast enough to fly from New York to Tokyo in under a minute. It is the fastest thing humanity has ever built. And even at that staggering speed, it would take over 6,000 years to reach Proxima Centauri. Our absolute fastest technology, the pinnacle of human engineering as of right now, would need 6,000 years to reach the nearest star. Not the center of the galaxy, not a distant nebula, just the star next door. And the Parker Solar Probe only achieved that speed because it was falling toward the Sun. Using the Sun's gravity to accelerate, it cannot sustain that speed heading outward into deep space. The moment it moves away from the Sun, gravity pulls it back, slowing it down. So here is the fundamental question this entire discussion revolves around. If getting to deep space is already almost impossibly difficult, what makes coming back even harder? Why is the return trip the real problem? The answer involves physics, biology, engineering, psychology, and time itself. Every single one of these factors works against you, and they do not just add up. They multiply. Each problem makes every other problem worse. By the end of this video, you will understand why some of the smartest people on this planet believe that deep space may be humanity's one-way door. We can push through it, perhaps, someday. But coming back through, that may be something the universe simply does not allow. Before we go further, if you are the kind of person who is genuinely fascinated by these deep questions about our universe, about what is really possible and what is not, then I need you to do something right now. Subscribe to this channel and hit the bell icon, because the kind of content we create here goes deep. Not surface-level clickbait, but real science, real data, real understanding. And drop a like on this video, because it tells the algorithm that people want this kind of thoughtful, detailed content. Now, let us continue. To understand why returning from deep space may be impossible, we first need to understand what deep space actually is. Most people hear the word space and think of astronauts floating in the International Space Station, or maybe the moon landings. But the ISS orbits at only about 408 kilometers above Earth's surface. That is less than the driving distance from Los Angeles to San Francisco. The moon is about 384,400 kilometers away. That is far by Earth standards, but in cosmic terms, it is right next door. NASA officially defines deep space as anything beyond 2 million kilometers from Earth's surface. But even that definition is, in a way, conservative. The real deep space, the space we are talking about today, begins when you leave the protective bubble created by our sun. You see, the sun does not just give us light and heat. It also creates an enormous magnetic bubble called the heliosphere. The sun constantly blasts out a stream of charged particles called the solar wind, and this wind pushes outward in all directions, inflating a bubble that extends far beyond the orbit of Pluto. This bubble, this heliosphere, acts as a shield. It deflects a significant portion of the deadly galactic cosmic rays that rain in from all directions in our galaxy. Research suggests the heliosphere blocks anywhere from 70 to 90% of incoming galactic cosmic radiation. Think about that. You are sitting inside a protective magnetic cocoon right now, shielded not just by Earth's atmosphere and magnetic field, but by the sun's heliosphere as well. You have layers upon layers of natural protection. The boundary of this bubble is called the heliopause. Voyager 1 crossed the heliopause in August 2012 at a distance of about 121 astronomical units from the Sun. Voyager 2 crossed it in November 2018 at about 119 AU. When they crossed that boundary, their instruments detected a dramatic shift. The solar wind dropped, galactic cosmic rays surged, the magnetic field changed direction. They had left the Sun's domain and entered interstellar space. And here is the critical thing. Beyond the heliopause, every protection you had is gone. No solar wind to deflect cosmic rays, no magnetic bubble to shelter inside. Just raw, unfiltered deep space, with its deadly radiation, its near absolute zero temperatures, and its incomprehensible emptiness. But the heliopause is just the beginning of what lies beyond. After you cross the heliopause, you enter the interstellar medium, the space between stars. And beyond that, at an estimated distance of 2,000 to 100,000 astronomical units from the Sun, lies the Oort Cloud, a vast, spherical shell of icy objects that marks the true outer boundary of our solar system's gravitational influence. The outer edge of the Oort Cloud is nearly 2 light-years from the Sun. That means Voyager 1, travelling at 17 kilometers per second, would need roughly 30,000 years just to reach the inner edge of the Oort Cloud, and another 30,000 years or more to pass through it. Our solar system is enormous beyond human comprehension, and everything beyond it is even more enormous. The voids between stars are staggering, the voids between galaxies are incomprehensible, and in all of that vast emptiness, there is nothing. No fuel stations, no repair docks, no communication relays, no gravity wells to slingshot around. Nothing but darkness and cold and silence. This is what deep space means. And this is why returning from it is such a fundamentally different problem from returning from, say, the Moon or even Mars. Now, let us talk about the single most important reason why returning from deep space may be impossible. It is called the Tsiolkovsky rocket equation, and it is the most beautiful and most cruel equation in all of space exploration. Konstantin Tsiolkovsky was a Russian scientist who, in 1903, the same year the Wright brothers achieved powered flight, derived a mathematical equation that describes how rockets work. The equation is elegant and simple, but its implications are devastating for deep space travel. In its simplest form, it says this: the amount of speed change a rocket can achieve depends on how fast its exhaust moves, and on the ratio of its total mass at the start to its total mass at the end, after the fuel is burned. The key word there is ratio. It is not a simple addition. It is exponential, and that changes everything. Here is what that means in plain language. A rocket moves forward by throwing stuff backward. That stuff is the exhaust from burning fuel. The faster you throw the exhaust backward, and the more of it you throw, the more your rocket speeds up. Simple enough. But here is the trap. The fuel itself has mass, and you need to carry that fuel with you at the start of the mission. So before you even launch, you need to accelerate not just your spacecraft and crew and supplies, but also all the fuel you will need for the entire mission. And that extra fuel makes your rocket heavier, which means you need more fuel to lift that extra fuel, which means you need even more fuel to lift that additional fuel, and so on and so on and so on. It is an exponential spiral. Every additional unit of speed you want requires exponentially more fuel. Let me give you a concrete example. NASA states that roughly 90% of the weight of a rocket going to orbit is propellant. Only 10% is the actual spacecraft, payload and structure. That means for every kilogram of stuff you want to put in orbit, you need about 9 kilograms of fuel. That is just to get to low Earth orbit, about 400 kilometers up, requiring a speed change of about 9.4 kilometers per second. Now let us scale this up. To go from low Earth orbit to Mars transfer orbit, you need an additional speed change of about 3.6 kilometers per second. To slow down and enter Mars orbit, another 0.9 kilometers per second. To land on Mars, about 1 kilometer per second more. To launch from Mars surface back into orbit, about 5.3 kilometers per second. And then to return to Earth from Mars orbit, several more kilometers per second. A complete round trip to Mars requires a total speed change, what engineers call delta V, of roughly 16 or more kilometers per second. And because of the exponential nature of the rocket equation, that does not mean twice the fuel of getting to orbit. It means vastly, enormously more fuel. But here is where it gets truly terrifying for deep space. To escape the solar system entirely, starting from low Earth orbit, requires a delta V of about 16.6 kilometers per second. That is a one-way ticket out of the sun's gravitational grip. Now, if you want to come back, you need to account for something that one-way probes never have to worry about. You need to slow down, stop, turn around, accelerate back, and then slow down again when you reach Earth. Very roughly, a return trip requires something like double the delta V of a one-way trip, and in some scenarios even more because you cannot use the tricks that work for outbound travel. Let us be conservative and say you need 30 kilometers per second of total delta V for a deep space round trip within the outer solar system with the best chemical rocket fuel we have, which has a specific impulse at around 450 seconds. The rocket equation tells us that the mass ratio required is approximately e to the power of 6.8, which is about 900. That means for every 1 kilogram of spacecraft that returns to Earth, you need to start with about 900 kilograms of fuel. If your spacecraft, with crew, life support, supplies, and structure, weighs 10,000 kilograms, you would need 9 million kilograms of fuel. That is more than the mass of 3 fully fueled Saturn V rockets, the largest rockets ever successfully launched. And that is just for a round trip within our own solar system. For an interstellar round trip, the numbers become so absurd they lose all meaning. To reach even 10% of the speed of light, and then slow down and come back, using chemical rockets, you would need a mass of fuel so large that it exceeds the mass of the observable universe. I am not exaggerating. The math is unforgiving. The exponential nature of the rocket equation makes interstellar return trips with chemical propulsion not just impractical, but physically impossible. You cannot carry enough fuel. You cannot build a big enough fuel tank. The fuel to carry the fuel to carry the fuel creates an infinite regression that collapses under its own weight. So what about better engines? What about ion drives, nuclear propulsion fusion reactors? These are real technologies, either existing or under serious development, and they do offer significant improvements. Ion thrusters, like those used on NASA's Dawn mission, have a specific impulse of about 3,000 seconds, roughly 7 times better than chemical rockets. This means they use fuel far more efficiently, but they produce incredibly low thrust. The Dawn spacecraft's ion engine produced about the same force as a single sheet of paper resting on your hand. It works in space because there is no friction, so even a tiny push, applied continuously for months or years, can build up significant speed. But even with ion drives, the fuel requirements for an interstellar round trip remain staggering. Better, yes. Feasible, no. Nuclear thermal propulsion, where a nuclear reactor heats hydrogen to produce thrust, roughly doubles the specific impulse of chemical rockets to about 900 seconds. NASA has been studying this for decades, under projects like MIRVA in the 1960s, and more recent programs. It would help for Mars missions, but it does not come close to solving the interstellar return problem. The mass ratios are still astronomical. Nuclear pulse propulsion, the idea behind Project Orion in the 1950s and 60s, proposed detonating small nuclear bombs behind a spacecraft and riding the shock waves. It would provide both high thrust and high specific impulse. Theoretical studies suggested it could reach a few % of the speed of light. But it was never built, it would violate nuclear test ban treaties, and even its most optimistic projections do not solve the return trip problem for interstellar distances. Fusion propulsion, using the same process that powers the Sun, would theoretically offer specific impulse in the range of 10,000 to 100,000 seconds. That would dramatically change the equation. But here is the reality. As of right now, no self-sustaining fusion reactor exists on Earth, let alone one compact and light enough to mount on a spacecraft. Fusion has been 20 years away for the last 60 years. We may achieve it someday, but we have not achieved it yet. And building a fusion rocket is an entirely separate and even harder engineering challenge than building a ground-based fusion reactor. The most exotic propulsion concept that has any grounding in real physics is antimatter propulsion. When matter and antimatter meet, they annihilate each other, converting 100% of their combined mass into energy. By comparison, nuclear fission converts about 0.1% of mass to energy, and nuclear fusion converts about 0.7%. Antimatter is, gram for gram, the most energy-dense substance possible, according to known physics. A single gram of antimatter, reacting with a gram of matter, would release energy equivalent to about 43 kilotons of TNT, roughly 3 times the Hiroshima bomb. With antimatter propulsion, the mass ratios for interstellar travel become manageable. You could, in theory, accelerate to a significant fraction of the speed of light with a reasonable amount of fuel. But the reality is sobering. The entire world's annual production of antimatter is measured in nanograms. A nanogram is a billionth of a gram. Producing a single gram of antimatter with current technology would cost approximately $25 billion and take millions of years. And storing antimatter is nearly as impossible as producing it, because it annihilates on contact with any normal matter. It must be suspended in a magnetic trap in a perfect vacuum, and the longest we have managed to store it is a matter of minutes for very small quantities. Antimatter propulsion is real physics, but it is not real engineering. Not yet. Not for centuries, possibly. So where does this leave us? With chemical rockets, an interstellar return trip is physically impossible. With ion drives, still impossible for interstellar distances. With nuclear thermal, still impossible. With nuclear pulse, theoretically marginally possible but never built, and probably never will be for political reasons. With fusion, may be possible if we can ever build a fusion rocket, which we have not done and cannot do yet. With antimatter, theoretically possible, but the production and storage challenges are so far beyond current technology that it might as well be magic. The rocket equation is not a suggestion, it is a law, and it says, with cold mathematical certainty, that returning from deep interstellar space is beyond anything we can currently build, or, in most scenarios, even theoretically design. But the fuel problem is only the beginning. Even if some miraculous breakthrough in propulsion solves the fuel issue, you still have to contend with the fact that deep space is unimaginably hostile to the human body. And I do not mean uncomfortable or challenging. I mean that deep space actively, relentlessly, methodically destroys the human body in multiple ways simultaneously. Let us go through them one by one. The first and most immediate effect of deep space on the human body is the loss of gravity. On Earth, gravity is constantly pulling on every cell, every bone, every muscle in your body. Your skeleton is strong because it has to support your weight. Your muscles are strong because they have to work against gravity every time you move. Your heart is strong because it has to pump blood upward to your brain against gravitational pull. In space, all of that disappears. And your body, which is ruthlessly efficient, responds by getting rid of what it does not need. Why maintain heavy, expensive bones if they are not bearing any weight? Why maintain large muscles if they are not lifting anything? Why keep a powerful heart if blood flows effortlessly in all directions? NASA research shows that astronauts lose approximately 1 to 2% of their bone mineral density per month in microgravity. On Earth, an elderly person might lose 1 to 2% per year. In space, you lose in 1 month what an elderly person on Earth loses in an entire year. Over a 6-month ISS mission, astronauts can lose up to 10% of their bone density. And here is the terrifying part. Not all of it comes back. Studies published as recently as 2025 tracking astronauts 4 years after their missions found that bone microarchitecture changes were still detectable long after return. Some bone loss appears to be permanent. Now extend this to a deep space mission lasting not 6 months, but 10 years, 20 years or more. The cumulative bone loss could be catastrophic. Bones could become so porous, so fragile, that they would fracture under the simple act of standing up in Earth's gravity. The skeleton that left Earth might literally be unable to support its owner upon return. Muscle loss follows a similar trajectory. Without the constant loading of gravity, muscles atrophy rapidly. Studies show that calf muscles can lose up to 20% of their mass in just 11 days in space. The body is cannibalizing its own muscle tissue because it sees no reason to maintain it. Astronauts on the ISS exercise for over 2 hours every day using specialized equipment, the Advanced Resistive Exercise Device for strength training, a treadmill with bungee cords to simulate weight, a cycle ergometer for cardiovascular fitness. And even with this grueling daily regimen, they still lose bone and muscle. The exercise slows the loss but does not prevent it. On a deep space mission lasting decades, exercise equipment would need to function perfectly for the entire duration. If a resistance machine breaks and cannot be repaired, the crew's physical deterioration accelerates, and there are no gyms in interstellar space, no replacement parts shipments, no sporting goods stores. The heart undergoes its own transformation in microgravity. On Earth, your heart works hard to pump blood upward to your brain against gravity. In space, blood flows freely in all directions, and the heart does not need to work as hard. So it weakens. Studies show the heart becomes more spherical in shape, and its performance declines. When astronauts return to Earth after months on the ISS, many experience orthostatic intolerance. They feel dizzy or faint when standing up, because their hearts cannot pump blood to their brains fast enough against Earth's gravity. This is after only 6 months. After years or decades in zero gravity, the heart might be so deconditioned that it simply cannot sustain consciousness in a gravitational field. An astronaut returning to Earth after a decades-long deep space mission could lose consciousness simply by standing up. And if the heart cannot deliver enough blood to the brain and organs under gravity, organ failure follows quickly. Then there are the eyes. This one might be the most disturbing because it was not even well understood until relatively recently. Astronauts on long-duration ISS missions began reporting vision problems. Their eyesight was getting worse. Some could not read their checklists. Some could not see instruments clearly. When scientists investigated, they discovered something alarming. In microgravity, the fluid inside the skull, the cerebrospinal fluid, redistributes. On Earth, gravity pulls this fluid downward. In space, it pulls around the brain and behind the eyes, increasing the pressure inside the skull. This increased intracranial pressure flattens the back of the eyeball and swells the optic nerve. The condition is now called Spaceflight-Associated Neuroocular Syndrome, or SANS. Over 60% of long-duration ISS astronauts have experienced some degree of vision change. Some of these changes persist even after return to Earth. On a multi-decade deep space mission, progressive vision degradation could lead to significant visual impairment or worse, with no eye doctors, no corrective surgery options, and no way to reverse the underlying cause. Perhaps the most haunting evidence of what space does to the human body comes from the NASA twin study. In March 2015, astronaut Scott Kelly launched to the International Space Station for a 340-day mission, while his identical twin brother Mark Kelly stayed on Earth. Because they share the same DNA, any differences that developed during Scott's time in space could be attributed to the space environment. The results, published in the journal Science in 2019, were striking. Scott Kelly experienced changes in gene expression, the way his DNA is read and used by his cells. About 7% of his gene expression changes did not return to normal even after he came back to Earth. His telomeres, the protective caps on the ends of chromosomes that typically shorten with age, actually lengthened in space, which was unexpected, but then they shortened rapidly after his return, which could be associated with accelerated aging. his gut microbiome changed. His cognitive performance showed some decline in the months after return. His DNA methylation patterns, which control which genes are turned on and off, were altered. And remember, this was only 340 days, less than a year. Imagine what would happen over 5 years, over 10 years, over 20 or 30 years in deep space. The genetic changes could be so extensive that the person who returns might be, on a molecular level, quite different from the person who left. The immune system adds another layer of danger. In space, the immune system becomes dysregulated. It does not function the way it does on Earth. Research has shown that dormant viruses reactivate in astronauts. Viruses that your immune system normally keeps suppressed, like herpes simplex, varicella zoster, the virus that causes chickenpox and shingles, Epstein-Barr virus, and cytomegalovirus, all show increased activity during spaceflight. T cells, the soldiers of your immune system, show decreased function. This means that a simple infection, something your body would normally fight off without you even noticing, could become life-threatening in space. And in deep space, there is no hospital, no pharmacy, no emergency room. If a crew member develops a serious infection, pneumonia, a dental abscess, appendicitis, they must be treated on board with whatever medical supplies are available. And those supplies degrade over time. Medications lose potency, antibiotics expire, surgical instruments have limited sterilization cycles. The medical reality of deep space is that you are on your own, with a weakened immune system, degraded medications, and no possibility of evacuation or resupply. So here is the horrifying composite picture for a return trip. An astronaut who has spent 10 or 20 years in microgravity attempting to return to Earth would face bones so weak they could fracture from the force of landing or even standing, muscles so atrophied they might not be able to support basic movement, a heart so deconditioned it might not sustain consciousness in gravity, eyes potentially damaged beyond recovery, an immune system that cannot fight basic infections, and a body whose very DNA has been altered in ways we do not fully understand. The body that left Earth might no longer be compatible with Earth. The astronaut might survive the journey home, but die upon arrival, killed not by space, but by their own home planet's gravity. And we have not even discussed the radiation yet. Radiation is the silent killer of deep space, and it may be the single most insurmountable biological barrier to a return trip. To understand why, you need to understand what kind of radiation exists in space, and why it is so different from anything we experience on Earth. On Earth, we are bathed in a small amount of background radiation from natural sources, about 2.4 millisieverts per year on average. This is harmless. Our bodies have evolved to repair the minor DNA damage caused by this level of radiation. We also have 2 layers of protection. First, Earth's magnetic field, the magnetosphere, deflects most charged particles from the Sun and from deep space. Second, our atmosphere, a thick blanket of nitrogen and oxygen extending hundreds of kilometers above us, absorbs most of the radiation that gets past the magnetic field. These 2 shields, working together, reduce our radiation exposure to nearly negligible levels. In space, these shields are gone. There are 3 primary sources of radiation in space. The first is solar particle events, or SPEs. These are bursts of high-energy protons ejected by the Sun during solar flares and coronal mass ejections. They come in sudden, intense waves and can deliver a potentially lethal radiation dose in a matter of hours to an unshielded astronaut. They are dangerous, but they are predictable to some degree, and astronauts can shelter in shielded parts of the spacecraft during events. The second source is trapped radiation in the Van Allen belts, zones of charged particles captured by Earth's magnetic field. These are only relevant near Earth and can be transited quickly. The third source, and by far the most dangerous for deep space travel, is galactic cosmic rays, or GCRs. Galactic cosmic rays are high-energy particles that originate outside our solar system, produced by violent cosmic events like supernovae, the explosions of dying stars. They consist primarily of protons, about 87%, with helium nuclei making up about 12%, and heavy ions, things like iron, carbon, and oxygen nuclei, making up about 1%. That 1% of heavy ions is the real killer. These particles travel at very close to the speed of light and carry enormous energy. When a single heavy ion, say an iron nucleus, passes through your body, it does not just nick a few cells. It tears through tissue like a microscopic cannonball, leaving a trail of destruction along its entire path. It shatters DNA molecules, kills cells outright, and damages surrounding tissue with secondary radiation from the impact. This type of radiation is called high linear energy transfer, or high-LET radiation, and it is qualitatively different from the radiation you get from an X-ray or even a nuclear bomb. It causes deep, targeted, hard-to-repair damage at the cellular level. And here is the critical problem. Galactic cosmic rays are incredibly difficult to shield against. On Earth, the atmosphere provides the equivalent of about 1,000 grams per square centimeter of shielding. That is roughly equivalent to a 10-meter thick wall of water above your head. In space, spacecraft walls provide nothing close to this. A typical spacecraft hull might offer 5 to 20 grams per square centimeter of shielding, 1/50th to 1/200th of what our atmosphere provides. And making the walls thicker does not solve the problem as simply as you might think. When high-energy galactic cosmic rays hit metal shielding, particularly aluminum, they do not just stop, they shatter into a spray of secondary particles, neutrons, protons, and other fragments that scatter in all directions inside the spacecraft. This is called secondary radiation or fragmentation, and in some cases, thick aluminum shielding can actually increase the radiation dose to the crew inside. You are not just failing to block the radiation, you are making it worse. The best passive shielding material identified so far is polyethylene, a common plastic that is rich in hydrogen atoms. Hydrogen is better at absorbing cosmic ray energy without producing as many dangerous secondary particles. But even polyethylene has limits. To reduce the galactic cosmic ray dose by roughly 50%, you would need about 20 grams per square centimeter of polyethylene shielding around the entire crew habitat. That adds thousands of kilograms to the spacecraft mass. And remember the rocket equation. Every kilogram of shielding means more fuel, which means more mass, which means even more fuel. The shielding problem and the fuel problem feed into each other in a vicious cycle. Monte Carlo computer simulations, which model radiation interactions particle by particle, show that even 400 grams per square centimeter of shielding, an extraordinarily thick barrier, cannot fully protect against the most energetic galactic cosmic rays. Some of these particles carry so much energy that they will pass through virtually any practical amount of shielding. Scientists have also proposed active shielding, using powerful electromagnetic fields to deflect charged particles away from the spacecraft, similar to how Earth's magnetic field works. This is physically sound in principle, but generating a magnetic field strong enough to deflect galactic cosmic rays requires superconducting magnets of enormous size and power, consuming large amounts of energy that may not be available in deep space, and adding significant mass and complexity to the spacecraft. No active radiation shielding system has been built or tested for spacecraft. So what does all this mean in terms of actual radiation exposure? On the International Space Station, which is partially protected by Earth's magnetic field, astronauts receive approximately 150 to 200 millisieverts of radiation per year. On a transit to Mars, which takes about 7 to 9 months and goes outside the magnetosphere, radiation exposure is estimated at about 300 millisieverts per year. In deep interstellar space, beyond the heliosphere where the sun's protective bubble no longer blocks galactic cosmic rays, the estimated exposure is 400 to 600 or more millisieverts per year. NASA's career radiation limit for astronauts is 600 millisieverts, which varies somewhat by age and sex. A deep space mission would exceed NASA's entire career limit within 1 to 2 years. On a 20-year round trip to the outer solar system or beyond, a crew member would accumulate something like 8,000 to 12,000 millisieverts or more of radiation exposure. To put that in perspective, an acute dose of 1,000 millisieverts causes radiation sickness. An acute dose of 5,000 millisieverts is lethal within weeks. The deep space doses are spread over years rather than delivered all at once, which the body tolerates better, but the cumulative effect is devastating. The long-term consequences include dramatically increased cancer risk, cardiovascular disease from radiation damage to blood vessels and the heart, cataracts from radiation damage to the lenses of the eyes, and neurological damage, including potential cognitive decline. Studies on animals exposed to simulated galactic cosmic ray radiation have shown brain inflammation, reduced cognitive function, and behavioral changes. The radiation does not just kill you quickly. It slowly, over years, degrades every system in your body. And it is not just the human body that suffers. Radiation also degrades the spacecraft's electronics. Every electronic device works by manipulating tiny electrical charges in circuits. When a galactic cosmic ray passes through a computer chip, it can deposit enough charge to flip a binary digit from a 0 to a 1, or vice versa. This is called a single event upset, or SIR, commonly known as a bit flip. A single bit flip in the wrong part of a computer's memory can corrupt data, crash software, or cause a system malfunction. In critical systems like navigation, life support control, or engine management, a bit flip could be catastrophic. Spacecraft electronics are typically radiation hardened, designed with larger transistors and redundant circuits to resist these effects. But radiation hardening makes electronics slower, heavier, and less capable than consumer electronics. Voyager 1's computers have only 68 kilobytes of memory each, roughly 1/1,000,000th the memory of a modern smartphone. But they have survived decades in space partly because their simple, robust design is inherently more resistant to radiation. Over decades in deep space, accumulated radiation damage degrades electronic components even beyond individual bit flips. Transistors gradually lose performance. Insulators break down. Circuit traces corrode at the atomic level. Memory cells fail permanently. Processors slow. An electronic system designed to last 15 years may be marginal at 20 and non-functional at 30. A return trip from deep space would depend on electronics that have been enduring radiation bombardment for the entire outbound journey. By the time you need them most, for the critical return navigation and engine burns, they may be at their most degraded and unreliable. Now, let us talk about something that does not get enough attention in discussions of deep space travel: communication. Because losing communication with Earth is not just an inconvenience. For a return trip, it could be the difference between finding your way home and drifting into the void forever. Radio signals travel at the speed of light. Nothing travels faster. This is not a limitation of our technology. It is a fundamental law of the universe, confirmed by over a century of experiments and observations. And the speed of light, while astonishingly fast by earthly standards, is agonizingly slow on cosmic scales. Light takes 1.3 seconds to reach the Moon. It takes 3 to 22 minutes to reach Mars, depending on where Mars and Earth are in their orbits. It takes 33 to 54 minutes to reach Jupiter. It takes over 4 hours to reach Neptune. It takes over 22 hours to reach Voyager 1. And it takes 4.24 years to reach Proxima Centauri. 4 years and 3 months for a one-way message. If you sent a question to a spacecraft at Proxima Centauri, you would wait 8.5 years for a response. That is not a conversation. That is a time capsule. NASA communicates with its deep space missions through the Deep Space Network, or DSN, a system of 3 ground stations located roughly 120 degrees apart around the globe: Goldstone in California's Mojave Desert, Madrid in Spain, and Canberra in Australia. This spacing ensures that at least one station can always see any direction in space as Earth rotates. Each station has large dish antennas, including 70-meter diameter behemoths that are among the most sensitive radio receivers on Earth. The DSN is an engineering marvel, but it is already strained. As of recent reports, the network is up to 40% oversubscribed, meaning there are more missions requesting antenna time than the network can provide. And the signal from distant spacecraft is incredibly faint. Signal strength decreases with the square of the distance. If you double the distance, the signal is 4 times weaker. If you go 10 times farther, the signal is 100 times weaker. Voyager 1's signal reaches Earth with a power of about 10 to the minus 16 watts, roughly 20 billion times weaker than a modern digital wristwatch battery. The DSN antennas can detect this only because they are enormously sensitive and because Voyager's signal is transmitted at a specific known frequency that the antennas are tuned to receive. At interstellar distances, the signal problem becomes qualitatively different. A spacecraft at Proxima Centauri would be about 250,000 times farther than Voyager 1 is now. The signal strength, following the inverse square law, would be about 62 billion times weaker than Voyager's already feeble signal. Detecting this would require receivers of extraordinary sensitivity, far beyond anything currently built. The Breakthrough Starshot project studied this problem extensively and identified it as one of the biggest elephants in the room. Even their most optimistic designs for tiny laser communication systems on the gram scale, probes could barely manage to signal back to Earth from 4 light-years away. And those probes were designed to be just communication devices, essentially. A crewed spacecraft would have more power available for communication, but also much greater distance to overcome for missions deeper into space. The bandwidth at extreme distances is crushingly low. Voyager 1 currently transmits data at about 160 bits per second. That is not a typo. 160 bits per second. A typical text message is about 1,000 bytes, or 8,000 bits. It would take Voyager 1 about 50 seconds to transmit a single text message. A single high-resolution photograph would take hours. At interstellar distances, where the signal is vastly fainter and the data rate correspondingly lower, meaningful communication becomes measured not in bits per second, but potentially in bits per day or bits per month. What does losing communication mean for a return trip? It means, most critically, losing navigation support. Currently, spacecraft in deep space are tracked by the DSN. Ground controllers send a signal to the spacecraft sends it back, and the round-trip time gives precise distance. The signal's direction gives angular position. This allows ground controllers to calculate the spacecraft's exact position and velocity, and upload course corrections. Without this ground-based tracking, a spacecraft must navigate autonomously. Some spacecraft have demonstrated autonomous navigation. NASA's Deep Space One mission tested a system called AutoNav that used onboard cameras to photograph known asteroids and stars and triangulate the spacecraft's position. But this works in the solar system, where there are many known reference objects at known positions. In interstellar space, the situation is radically different. The star field changes very slowly as you move between stars. Stars that were your reference points from Earth look different from another position light years away due to parallax. Your star maps, preloaded before the mission, may not match what your cameras actually see, and the precision required is extraordinary. Earth, from a distance of 4 light years, subtends an angle of about 0.0000003 degrees. Missing your aim by even a tiny fraction of a degree means missing the entire solar system by billions of kilometers. Navigation errors compound over time and distance. A 0.001 degree error over 4 light years translates to missing your target by roughly 70 billion kilometers. That is nearly 500 times the distance from Earth to the Sun. You would sail right past the solar system without even knowing it. Scientists have proposed using pulsars, rapidly rotating neutron stars that emit extremely precise and regular pulses of radio and X-ray radiation, as cosmic lighthouses for navigation. NASA tested this concept with the Sextant experiment on the ISS, demonstrating positioning accuracy within about 5 kilometers using X-ray pulsar timing. This is promising, but 5-kilometer accuracy in Earth orbit is very different from 5-kilometer accuracy at interstellar distances. The pulsars themselves are at varying distances and directions, and the timing precision required for interstellar navigation pushes the limits of onboard instrumentation that, remember, is being degraded by decades of radiation exposure. The navigation problem alone might make a return trip impossible, even if you somehow solved every other problem. Now I want to take you somewhere that most discussions of deep space travel skip over, and it might be the most important factor of all, the human mind. Because even if you solve the fuel problem, even if you protect the body from radiation, even if you build a spacecraft that lasts for decades, you still have to keep the people inside it sane, and deep space may be the most psychologically hostile environment that a human being could ever experience. We know quite a lot about what isolation and confinement do to people, even on Earth. The Mars 500 experiment, conducted from 2010 to 2011 in Moscow, locked 6 crew members inside a simulated spacecraft for 520 days, about 17 months, to study the psychological effects of a Mars duration mission. The crew never left the building. They had communication delays simulated to match Mars distances. They had limited supplies, limited space, and only each other for company. The results were sobering. Crew members developed sleep disorders. Some showed signs of depression. Cognitive processing slowed. Interpersonal conflicts arose and worsened over time. One crew member spent nearly his entire Mars surface simulation period in bed, essentially checking out psychologically. And these were highly motivated, carefully selected individuals who knew they were in a simulation and could leave in an emergency. The psychological effects on a real deep space crew, who know they truly cannot leave, who know that no rescue is possible, would likely be far more severe. Research on isolated groups, including Antarctic winter-over crews who spend months in darkness and confinement, submarine crews on extended patrols, and participants in isolation experiments, has identified a pattern called the third quarter phenomenon. Morale and performance tend to dip significantly around the 75% mark of any isolated mission. This is when the initial excitement has worn off, the end is not yet in sight, and the monotony and confinement become most oppressive. On a 6-month ISS mission, the third quarter is a few weeks of difficulty. On a deep space mission lasting 20 years, the third quarter would last 5 years. 5 years of deepening psychological distress, with no possibility of relief, no visitors, no change of scenery, no fresh air, no sunshine, no nature, no escape. Consider what daily life would be like for a crew on a decades-long deep space mission. You wake up in the same tiny cabin you have slept in for years. You see the same faces, eat the same reconstituted food, breathe the same recycled air, walk the same corridors, perform the same maintenance tasks. You look out the window and see nothing. Not the beautiful blue curve of Earth, not the cratered surface of the Moon, not even the dim ruddy disk of Mars. Just blackness, stars that do not change position. A void so vast and empty that the human mind, which evolved on the plains of Africa surrounded by trees and rivers and other people, has no framework for processing it. Research published in Frontiers in Psychiatry documents that even astronauts on 6-month ISS missions experience emotional dysregulation, cognitive dysfunction, and disrupted sleep-wake rhythms. The ISS is only 400 kilometers from Earth. The crew can look out the window and see their home planet. They can video call their families with only a slight delay. They know that in an emergency, a Soyuz capsule can bring them home in hours. In deep space, all of these psychological anchors are gone. Psychologists have discussed what they call the overview effect, the profound sense of awe and interconnectedness that astronauts report when they see Earth from space. It is described as life-changing, a shift in perspective that makes national borders and conflicts seem petty against the backdrop of our fragile blue planet. But what happens when that blue planet is no longer visible? When Earth becomes just another faint star, indistinguishable from the millions of others? Some researchers have theorized about a deep space effect, or an abyss effect, the psychological impact of being so far from Earth that it can no longer be seen. No human has experienced this yet, so we can only speculate based on what we know about extreme isolation and sensory deprivation. But the implications are concerning. Complete detachment from home, from humanity, from everything familiar. The realization, visceral and inescapable, that you are the most isolated humans who have ever lived. That the nearest other person outside your crew is billions or trillions of kilometers away. That if you screamed, no one would hear you for years. This is not an environment that the human mind was designed for. Communication delays compound the psychological burden. NASA research has shown that communication delays significantly impact crew behavior and performance. At Mars distances where a message takes 20 minutes each way, real-time conversation is impossible. Psychological support from Earth becomes asynchronous, more like exchanging letters than having a conversation. A crew member in crisis cannot speak to a therapist in real time. They send a message describing their distress and wait 40 minutes or more for a response. At interstellar distances, this delay stretches to years. A message sent from a spacecraft halfway to Proxima Centauri would not reach Earth for over 2 years. The response would not arrive for 2 more years. The crew would be utterly alone, dependent entirely on their own psychological resources, and whatever automated mental health tools are on board. Whether human beings can remain psychologically stable under such conditions for decades is an open question that no one can answer because it has never been tested. Now let us talk about keeping the crew alive. because even a psychologically healthy crew will die if the life support systems fail. On the International Space Station, the Environmental Control and Life Support System, or ECLSS, is one of the most complex systems aboard. It recycles about 90% of the water on the station. Urine, sweat, and humidity from the air are all collected, processed, and purified back into drinkable water. Oxygen is generated by electrolysis, splitting water molecules into hydrogen and oxygen, using electricity from the solar panels. Carbon dioxide is removed from the air by chemical scrubbers, and the Sabatier system converts some of the captured CO2 and hydrogen into water and methane, recovering additional water. It is a sophisticated system, but it is not a closed loop. The ISS still requires regular resupply missions from Earth, approximately 5,000 to 7,000 kilograms of supplies per crew member per year. Fresh food, replacement filters, spare parts, gases, chemicals, new equipment. Without these resupply missions, the ISS would become uninhabitable within months. A deep space mission beyond Mars would receive no resupply, zero. The distances are too great, the travel times too long. Everything the crew needs for the entire mission, which could be decades, must either be carried from the start or produced on board. This requires what engineers call a 100% closed-loop life support system, and no one has ever built one that works. The most famous attempt was Biosphere 2, a massive sealed ecosystem built in the Arizona desert in the early 1990s. It enclosed 3.14 acres under glass and steel, containing miniature versions of Earth's biomes: a rainforest, an ocean, a desert, a savanna, agricultural land. 8 people were sealed inside for 2 years, starting in 1991. The goal was total self-sufficiency. It failed spectacularly. Oxygen levels dropped from 21% to 14.2%, equivalent to the thin air at an altitude of 4,000 meters. Carbon dioxide levels spiked. The concrete structure absorbed oxygen through an unexpected chemical reaction. Food production was inadequate, and the crew was chronically hungry. Ant and vine species overran sections of the ecosystem, disrupting the balance. Pollinating insects died off. The crew came close to needing emergency oxygen supplies from outside. Biosphere 2 had every advantage: Earth's gravity, Earth's sunlight, Earth's temperature range, and the ability to open the doors if things went truly wrong. It still failed. Building a closed-loop ecosystem that can sustain humans in a spacecraft, in zero gravity, in deep space, for decades, is a challenge of an entirely different order. Food is a particularly thorny problem. NASA research indicates that most space food maintains acceptable nutritional quality for approximately 3 to 5 years. After that, vitamins degrade, especially vitamins A, C, B1, and folic acid. Fats go rancid. Texture and taste deteriorate. A deep space mission lasting 20 years cannot simply carry 20 years of food, because much of it would be nutritionally worthless by the time it was needed. The alternative is growing food on board. Hydroponics, algae cultivation, possibly insect farming. But growing food in space requires controlled lighting at specific wavelengths and intensities, a reliable water supply, nutrient solutions, CO2 management for photosynthesis, waste recycling, and significant crew time for maintenance. No space-based food production system has ever been demonstrated to fully sustain a human crew. NASA has grown lettuce and radishes on the ISS in small experimental chambers, but scaling this to full nutritional self-sufficiency is a massive leap. Water and air recycling systems degrade over time. Filters clog, membranes develop holes or become fouled by microbial growth. Pumps wear out. Seals dry and crack. Sensors drift out of calibration. Even if a recycling system achieves 99% efficiency, the 1% loss per cycle means a slow but inexorable bleeding of your water and air supply. Over months, the loss is manageable. Over decades, it becomes critical. Spare parts must be carried or manufactured on board. Manufacturing replacement parts in space requires tools, raw materials, and expertise. 3-dimensional printing technology is improving, but printing complex components like filter membranes or pump impellers in zero gravity from limited materials is far from routine. Energy is another existential concern. The ISS runs on solar power, with arrays generating 75 to 90 kilowatts. But solar power has a hard distance limit. The intensity of sunlight decreases with the square of the distance from the Sun. At Mars, orbit roughly 1.5 astronomical units from the Sun, solar intensity is about 43% of Earth's level. At Jupiter, 5.2 AUU, it drops to about 3.7%. At Saturn, 9.5 AU NATO, it is about 1.1%. Beyond Jupiter, solar panels become impractical. They simply cannot generate enough power to sustain a spacecraft's systems. Deep space missions like Voyager and New Horizons use radioisotope thermoelectric generators, or RTGs, which convert the heat from the natural radioactive decay of plutonium-238 into electricity. RTGs are reliable and long-lasting, but they have two critical limitations. First, they produce very little power. Voyager 1's 3 RTGs originally generated about 470 watts in 1977. By 2025, due to the decay of the plutonium and the degradation of the thermoelectric couples that convert heat to electricity, they produce only about 220 watts, less than enough to power 3 standard incandescent light bulbs. By around 2030, the power output will likely drop below the minimum needed to operate any instruments, and Voyager will go silent forever. The half-life of plutonium-238 is 87.7 years, meaning that after 87.7 years, only half the fuel remains, and after 175 years, only a quarter. Power output declines steadily and irreversibly. Second, plutonium-238 is extremely rare and expensive to produce. The United States currently produces only about 1.5 kilograms per year, and a single RTG unit uses several kilograms. For a deep space mission requiring thousands of watts of power over decades, you would need many RTGs adding substantial mass. The alternative is nuclear fission reactors, miniaturized versions of the power plants on Earth. NASA has developed prototypes like the kilopower reactor, which can generate 1 to 10 kilowatts of electrical power using enriched uranium. These could provide more power than RTGs and last longer, but they add complexity, mass, radiation risk from the reactor itself, and potential points of failure. No fission reactor has ever operated in space for an extended mission, though tests have been conducted. There is also the issue of cryogenic fuel storage. Many advanced propulsion concepts require cryogenic fuels, liquids stored at extremely low temperatures, like liquid hydrogen at -253 degrees Celsius. In space, these fuels slowly boil off, even in insulated tanks, because perfect insulation does not exist. NASA's zero boil-off tank experiments are trying to solve this problem, but as of their published results, preserving cryogenic fuels in space beyond several days without active cooling systems is not yet possible. On a mission lasting decades, even a tiny boil-off rate means that fuel gradually disappears. By the time you need it for the return trip, it may be gone. Now, let us consider the spacecraft itself as a machine, because machines break. Everything breaks. The second law of thermodynamics, the law of entropy, states that the disorder in any closed system inevitably increases over time, unless energy is spent to maintain order. A spacecraft is a closed system, and in deep space the forces working to destroy it are relentless. All materials degrade, metals slowly corrode, even in the vacuum of space, through processes like atomic oxygen erosion near Earth and radiation-induced embrittlement in deep space. Polymers, the plastics and rubbers used in seals, insulation, wiring coatings, and structural components, become brittle under long-term radiation exposure. They crack, they flake, they lose their elasticity. Lubricants that keep moving parts functioning, things like gyroscope bearings, valve mechanisms, and solar panel gimbals, slowly evaporate in vacuum through a process called outgassing. Seals that keep air in and space out dry and shrink over years, developing micro-leaks. Thermal cycling, the constant alternation between extreme heat when facing the sun and extreme cold when in shadow, stresses materials through expansion and contraction, eventually causing fatigue cracks. The International Space Station has been in orbit since 1998, and it requires constant maintenance. Astronauts spend a significant portion of their time repairing and replacing components. External spacewalks are conducted regularly to patch holes, replace equipment, and maintain the station's structure. Without this continuous human maintenance, the ISS would have failed years ago. A deep space spacecraft would need to be self-maintaining for decades, something no spacecraft has ever been designed to do. And the repairs become harder as spare parts are consumed and tools wear out. In interstellar space, even the empty space itself is hostile to a moving spacecraft. The interstellar medium, the thin gas and dust between stars, contains about 1 atom per cubic centimeter, mostly hydrogen. That sounds incredibly empty, and it is. But at high velocities, even individual atoms become dangerous. If a spacecraft is moving at 10% of the speed of light, which is 30,000 kilometers per second, each hydrogen atom it encounters is, from the spacecraft's perspective, a projectile hitting it at 30,000 kilometers per second. At those velocities, the kinetic energy of each atom is comparable to that of a particle in a particle accelerator. Impact after impact, atom after atom, trillions and trillions of them over years of travel, slowly erodes the spacecraft's leading surface. Research published in the Astrophysical Journal in 2022 found that at relativistic speeds, interstellar medium gas bombardment can damage a spacecraft's surface to a depth of approximately 0.1 millimeters for quartz-like material after a single interstellar transit. That may sound small, but it is significant for sensitive instruments, optical surfaces, and thin structures. Over a round trip, the damage doubles. Antennas, sensors, camera lenses, and solar collectors on the spacecraft's leading surface would be gradually sandblasted by invisible atomic hail. Micrometeorites and dust grains pose an even more acute threat. In interstellar space, these are sparse but not absent. A grain of dust weighing a milligram, traveling at even a modest relative velocity of 15 kilometers per second, carries the kinetic energy of a bullet. At higher velocities, the energy scales with the square of the speed. ESA research documents that hypervelocity impacts at speeds of 15 to 72 kilometers per second can allow even millimeter-sized particles to penetrate spacecraft walls and seriously damage internal equipment. The space shuttle, operating in low Earth orbit, where debris density is relatively high, suffered numerous micrometeorite impacts during its career, including window damage that required replacement. In interstellar space, the debris density is much lower, but the travel time is much longer. Over decades, even rare impacts accumulate. A single unlucky hit on a critical component, a fuel line, a window, a computer, a pressure vessel, could be catastrophic, with no possibility of external repair. Thermal management in deep space presents its own challenges. The temperature of interstellar space, defined by the cosmic microwave background radiation, is about 2.7 Kelvin, or minus 270.45 degrees Celsius. This is astonishingly cold, only 2.7 degrees above absolute zero, the theoretical minimum temperature where all atomic motion ceases. A spacecraft in deep space, far from any star, will radiate its internal heat into this frigid void. Without active thermal management, exposed surfaces will cool toward this temperature, which would freeze propellants, crack materials, and kill electronic systems. Conversely, electronics and life support systems generate heat that must be dissipated to prevent overheating. On the ISS, large radiator panels radiate excess heat into space, but radiators work less efficiently in deep space because the temperature difference between the radiator and the environment is smaller when the spacecraft is already very cold. Thermal management systems use fluid loops, heat exchangers, and phase change materials, all of which can leak, clog, or degrade over time. A thermal system failure in deep space means either the crew freezes or the electronics overheat. Neither is survivable. So here is the picture for the spacecraft on a return trip. A machine that has been in the most hostile environment imaginable for decades. Its hull eroded by interstellar medium bombardment and micrometeorite impacts. Its seals dried and cracked. Its lubricants evaporated. Its electronics degraded by cumulative radiation exposure. Its power systems producing less energy every year as radioisotope fuel decays. Its thermal management systems aging and losing efficiency. Its life support components worn from years of continuous operation. This is the vehicle that must now execute the most demanding maneuver of the mission, the return. It must fire engines that may not have been used in years and may be unreliable. It must navigate with instruments whose accuracy has degraded. It must protect its crew with shielding that has been battered and thinned. It must sustain life support for another journey of equal or greater duration. The machine that left Earth at the peak of its capability is now a shadow of itself, and it must somehow accomplish a task that was already at the edge of possibility when it was brand new. Let me talk about time now, because time is perhaps the most poetically cruel of all the barriers. The universe is vast, and we are slow. Even the fastest technologies we can currently envision would require decades or centuries for interstellar travel. But human beings do not live for centuries. We live for decades. The average global life expectancy is about 73 years. Even the healthiest, most genetically fortunate human will rarely live past 100. This means that for interstellar travel at any speed we can currently imagine, the travel time exceeds, or at least consumes, a significant portion of a human lifespan. If we could achieve 10% of the speed of light, which is 30,000 kilometers per second, a speed that no current technology can reach, and that would require revolutionary propulsion systems. The one-way trip to Proxima Centauri would take about 42 years. An astronaut who leaves Earth at age 30 would arrive at age 72, assuming they survive the journey in reasonable health, which we have already discussed is far from certain. They would have no healthy years left for a return trip. At 1% of the speed of light, 3,000 kilometers per second, the trip takes about 424 years, one way. That is roughly 5 to 6 human lifetimes. A round trip at this speed would take about 850 years. At Voyager 1's speed of 17 kilometers per second, the trip takes 73,000 years one way. A round trip is 146,000 years. For context, anatomically modern humans have existed for about 300,000 years. The entire history of agriculture is about 12,000 years old. The Roman Empire fell 1,500 years ago. A 146,000-year round trip spans a significant fraction of our entire species' existence. Some people point to time dilation, the effect predicted by Einstein's special relativity, where time passes more slowly for objects moving at high speeds relative to a stationary observer, as a potential solution. And it is real. It has been measured and confirmed with atomic clocks on aircraft and satellites. But its effects are tiny at any speed we can currently achieve. At 10% of the speed of light, the time dilation factor is only about 1.005. Time would pass about 0.5% slower for the traveler. On a 42-year trip, you would save about 10 weeks. At 50% of the speed of light, the dilation factor increases to about 1.15. Time passes about 13% slower. A 42-year trip from Earth's perspective would feel like about 37 years to the traveler. Better, but not transformative. At 90% of the speed of light, the factor reaches about 2.29. A 42-year trip from Earth's perspective would feel like about 18 years to the traveler. This is significant, but reaching 90% of light speed requires energy quantities that beggar the imagination. At 99% of the speed of light, the factor is about 7.09. A 42-year trip would feel like about 6 years, but 99% of light speed is so far beyond any current or foreseeable technology that it is essentially a thought experiment. And here is the catch that people often miss about time dilation. Even if you could travel fast enough for it to matter, it creates a new problem for the return trip. If you travel to Proxima Centauri at 99% of light speed, about 6 years pass for you, but about 8.5 years pass on Earth for each leg of the journey. A round trip would mean about 12 years of your life, but 17 or more years on Earth. At even more extreme speeds, the discrepancy grows. A round trip at 99.9% of light speed might feel like a few years to you, but decades or centuries would pass on Earth. You would return to find that everyone you knew was old or dead. The world you left would be unrecognizable. You would be a stranger in your own home. Time dilation does not solve the return problem. It transforms it into something arguably even more tragic. You can go and come back, but you cannot come back to what you left. The concept of generation ships is sometimes proposed as a solution to the time problem. If a single human lifespan is too short for interstellar travel, why not build a ship large enough to sustain a community of people who live, reproduce, raise children, grow old, and die during the voyage? Their descendants would eventually arrive at the destination. This is a real concept that serious scientists have studied, but the challenges are immense. Genetic research suggests that a minimum viable population for multi-generational spaceflight, one that avoids the genetic bottleneck of inbreeding, would need at least 500 to several thousand individuals. These people would need a self-sustaining economy, a food production system, water and air recycling, governance, education, conflict resolution, medical care, and a social structure that remains stable over centuries. No human society in history has remained stable for centuries in isolation, and the people born on this ship, who have never seen Earth, never felt wind on their face, never swum in an ocean, never walked through a forest, would they even want to return to a planet they have never known? The generation ship concept does not solve the return problem. It transforms the mission from a round trip into a permanent exodus. Equipment lifespan adds another dimension to the time problem. Most spacecraft are designed for missions lasting 5 to 15 years. The ISS was designed for a 15-year operational life and has been extended through continuous maintenance and component replacement. Voyager 1 and 2 have lasted nearly 49 years, which is extraordinary, but they are approaching the end of their functional lives as their RTG power dwindles. No spacecraft has ever been designed to last 50 to 100 years while maintaining the performance needed for human life support and precision navigation. We do not have the engineering experience to build machines with that kind of longevity. We do not fully understand how materials and systems degrade over such timescales in the space environment. A return trip from deep space would require equipment to function reliably for the entire outbound journey, plus the entire return journey. Potentially 40 to 100 or more years of continuous operation. This is beyond any current engineering capability. Now, let me tell you about navigation, because even if you solve every other problem, if you cannot find your way home, none of it matters. Navigation in deep space is not like navigation on Earth, or even in our solar system. On Earth, you have GPS satellites, landmarks, road signs, maps. In the solar system, NASA's Deep Space Network tracks spacecraft with extraordinary precision using radio signals. Ground controllers know where every spacecraft is to within a few kilometers, even at the distance of Pluto. They can calculate trajectories, plan course corrections, and upload instructions. This works because the solar system is full of known reference points, planets, moons, asteroids, the sun itself, and because the DSN can maintain communication. In interstellar space, all of this falls apart. The familiar reference points of the solar system shrink to invisibility. Earth itself, the target for a return trip, cannot be seen with the naked eye from interstellar distances. Even with a telescope, it would be a tiny, faint dot, lost among billions of other faint dots. The sun would be just another star, not particularly bright or distinctive from a few light years away. And the star field itself, the pattern of stars visible from the spacecraft, would be different from the patterns catalogued on Earth because the stars are at different distances and the spacecraft has moved to a different vantage point. Stars that appeared close together from Earth might appear farther apart from another location, and vice versa. This effect, called parallax, is useful for measuring distances to nearby stars from Earth, but it complicates navigation from a moving spacecraft because the star maps from Earth do not directly match the view from interstellar space. Autonomous navigation systems would need to identify stars, calculate their positions from the spacecraft's current location, determine the spacecraft's position and velocity in three-dimensional space, predict where Earth and the Sun will be when the spacecraft arrives back in the solar system years or decades later, and compute the precise trajectory to get there. All of this must be done with instruments that have been degraded by years of radiation and micrometeorite impacts, with computers that may have suffered bit flips and component failures, and with no possibility of verification or correction from Earth. The precision required is staggering. Earth, from a distance of 4 light years, subtends an angle of roughly 0.00000003 degrees. Even a 0.001 degree error in aiming, accumulated over 4 light years of travel, would cause the spacecraft to miss the solar system by roughly 70 billion kilometers. That is hundreds of times the distance from Earth to the Sun, The spacecraft would sail past in the dark, never knowing it had missed, continuing into the void until its power failed and its occupants perished. Pulsar navigation offers some hope. Pulsars are rapidly spinning neutron stars that emit beams of electromagnetic radiation, like cosmic lighthouses. Because their rotation is extremely regular, the timing of their pulses can be used as a kind of cosmic GPS. NASA has tested this with the Sextant experiment, which demonstrated positioning within about 5 kilometers using X-ray pulsar timing. But interstellar navigation requires far greater precision than 5 kilometers, and the instruments needed to detect and time pulsar signals must remain functional and calibrated over the entire mission. This is possible in principle, but untested in practice, and the challenges of maintaining instrument precision over decades of radiation exposure are significant. Let me now take all of these abstract problems and ground them in reality by looking at actual missions that illustrate what we are talking about. Let us start with Voyager 1 and Voyager 2, the two farthest-traveled human-made objects in existence. Launched in 1977, they were designed to explore the outer planets of our solar system, Jupiter, Saturn, and in Voyager 2's case, Uranus and Neptune as well. They accomplished their primary mission spectacularly, and then just kept going. Voyager 1, as of early 2026, is about 173 AU from Earth, over 25.8 billion kilometers. Voyager 2 is about 146 AU away. Both have crossed the heliopause and entered interstellar space. They are the ultimate one-way travelers. They carry no fuel for course changes or return. Their ion engines, or rather their hydrazine thrusters used for attitude control, have limited fuel remaining. Their RTGs are dying. Voyager 1's power output is roughly 220 watts and declining about 4 watts per year. By 2030, the power will likely be insufficient to operate any scientific instruments, and the spacecraft will go silent. They will then drift, powerless and dark, through interstellar space for millions, perhaps billions of years. They carry the famous golden records, gold-plated copper discs containing sounds and images from Earth, including greetings in 55 languages, samples of music from around the world, sounds of nature, and 115 images depicting life on our planet. The records were included because the mission designers understood, with perfect clarity, that these spacecraft would never come home. The golden records are messages in bottles, cast into an infinite ocean on the vanishingly small chance that someday something or someone might find them. Even if we wanted to bring them back, we could not. They have no return fuel. They are traveling in directions that do not lead back to Earth without enormous course changes. And they are so far away that a rescue mission would take decades to reach them and decades more to return, assuming propulsion technology that does not exist. New Horizons, launched in January 2006, was the fastest spacecraft at launch, leaving Earth at about 58,536 kilometers per hour. It reached Pluto in July 2015, after 9.5 years of travel, conducting a brilliant flyby that revealed Pluto's heart-shaped nitrogen ice plain and its complex geology. Then it continued outward, passing the Kuiper Belt object Arrokoth in January 2019. Now approximately 60 or more AU from Earth and heading deeper into the outer solar system. Like the Voyagers, it is a one-way mission with no return capability. It too will eventually lose power and fall silent. Another dark, cold artifact drifting endlessly between the stars. Apollo 13 provides perhaps the most visceral illustration of how difficult returning from deep space can be. In April 1970, the Apollo 13 crew, Jim Lovell, Jack Swigert, and Fred Hayes, were on their way to the moon when an oxygen tank in the service module exploded. They were approximately 320,000 kilometers from Earth. The explosion crippled the spacecraft's power and life support systems. The crew was forced to use the lunar module as a lifeboat, a system designed for 2 people for 2 days, now supporting 3 people for 4 days. They used the moon's gravity to slingshot back toward Earth. They had to perform precise engine burns with limited fuel and failing systems. Carbon dioxide built up dangerously inside the spacecraft, and the crew had to improvise a filter adapter from available materials. Temperatures dropped near freezing. Water was rationed to a few ounces per day. They made it back. Barely. It is rightly called a successful failure, but consider the advantages they had. They were only 1.3 light seconds from Earth. Communication was in real time, with ground controllers able to calculate solutions and relay them immediately. They had the moon available for a gravity assist to redirect them back toward Earth. They were within Earth's gravitational sphere of influence, meaning Earth's gravity was actively pulling them back. They had a spacecraft that was only days old and at full performance except for the damaged systems. Mission Control in Houston, staffed by hundreds of engineers, worked around the clock to solve every problem. Now imagine the same scenario in deep space. An explosion 10 billion kilometers from Earth, communication delay of 9 hours each way, no moon for a gravity assist, no gravitational pull toward home. A spacecraft that has been operating for years and is partially degraded, no real-time support from mission control. Under those conditions, Apollo 13's crew would have died. Without question, the distances, delays, and lack of resources make survival, let alone return, effectively impossible. Consider Mars. Even a round trip to Mars, which is within our own solar system, is considered one of the most challenging endeavors in the history of human exploration. The trip takes approximately 7 to 9 months each way, using current propulsion technology, including the time astronauts must wait on Mars for the planets to realign for a return trajectory. A round trip takes about 2 to 3 years total. NASA's reference missions describe approximately 900-day total mission durations. And even for this relatively short trip, the challenges are considered extreme. Radiation exposure during the transit exceeds what astronauts receive in a year on the ISS. Psychological challenges of isolation and confinement over years are a major concern. Food and supply mass must be carefully minimized. Communication delays of up to 22 minutes each way limit real-time support. And this is for a destination that is, at its closest, only about 55 million kilometers away. Deep interstellar space is measured in trillions of kilometers. If we are struggling, after decades of planning and billions of dollars in investment, to execute a round trip to a planet in our own solar system, the gap between that and interstellar return capability is not a step. It is a chasm. The story of Breakthrough Starshot crystallizes many of these themes into a single, real-world example. In April 2016, Russian-Israeli billionaire Yuri Milner announced a $100 million initiative to develop the technology for an interstellar probe. Standing beside him at the press conference at One World Observatory in New York were Stephen Hawking, Freeman Dyson, and other luminaries of science. The plan was elegant in concept. Build a massive array of ground-based lasers capable of generating 100 gigawatts of power. Use these lasers to push tiny light sails, spacecraft weighing about a gram each, to 20% of the speed of light. At that speed, they would reach Alpha Centauri in about 20 years. The light sails would conduct a brief flyby, snapping pictures and taking measurements, then transmit their findings back to Earth using tiny onboard lasers, using the Sun as a beacon to aim toward. It was the most serious and best-funded interstellar mission concept in history. Dozens of research groups were assembled. Progress was made on several fronts. Scientists demonstrated laser beam combining with tens of lasers in the lab, identified silicon nitride as a potential light sail material that could be fabricated at submicron thickness, developed computer simulations of light sail behavior during acceleration, and successfully launched and communicated with 105 tiny ChipSat spacecraft in orbit. But the challenges proved enormous. The laser array would need millions of individual lasers working in perfect synchronization, with real-time adaptive corrections for atmospheric turbulence. The light sail would need to withstand 40,000 G of acceleration and 100 gigawatts of laser energy without melting or tearing. Communication from 4 light-years away using a gram-scale transmitter was identified as perhaps the biggest unsolved problem. The cost of laser power would need to drop by a factor of 2,000 to 10,000 from current prices to be feasible, and a 100 gigawatt laser is functionally a weapon of unprecedented power, raising political and diplomatic complications. And even this most ambitious plan, the most audacious interstellar project ever seriously attempted, never considered a return trip. The light sail probes would fly past Alpha Centauri at 60,000 kilometers per second and just keep going. They cannot slow down. There is nothing at the destination to slow them. and they carry no onboard propulsion. They would blaze through the Alpha Centauri system in a matter of hours, snapping what pictures they could, and then continue into the void forever. The Breakthrough Starshot concept is, fundamentally, a one-way trip. The project's designers understood this from the start. It was not a limitation they hoped to overcome, it was a fundamental constraint of the physics. And even this one-way mission, which does not need to solve any of the return trip problems, proved too difficult and expensive to realize. By 2025, the project was effectively on indefinite hold. The $100 million was never fully deployed. Only about $4.5 million was actually distributed across approximately 30 research contracts. The project's executive director described it as on hold. Several participating scientists told journalists they had not heard from the project leadership in years. The most serious attempt to reach the stars, backed by a billionaire's fortune and the endorsement of some of the greatest scientific minds of our era, quietly faded away, defeated by the sheer difficulty of doing even a one-way trip. So let us now consider the proposed solutions. What ideas have scientists put forward to overcome these barriers? And how close are they to reality? We owe it to intellectual honesty to examine these ideas seriously, neither dismissing them nor overhyping them. Artificial gravity is one of the most promising concepts for addressing the biological degradation caused by microgravity. The idea is simple. Spin a spacecraft or a section of it to create centrifugal force that mimics gravity. This is well-established physics. Any rotating object creates a centrifugal force that pushes outward from the center of rotation. If a crew habitat is placed at the outer edge of a rotating structure, the crew inside would feel a force pushing them toward the floor that functions much like gravity. The concept was popularized in science fiction, from the rotating space station in 2001: A Space Odyssey to the Hermes spacecraft in The Martian. The engineering, however, is less simple. To create comfortable artificial gravity without causing disorientation from Coriolis effects, which is the dizzying sensation caused by the rotation, the radius of the spinning structure needs to be large, typically estimated at 100 meters or more, for a rotation rate that generates 1 g without causing motion sickness. Building a 100-meter radius rotating structure in space, transporting it to deep space, and integrating it with propulsion and life support systems would be an extraordinary engineering challenge. No rotating artificial gravity system has ever been built or tested in space, not even a small one. It remains entirely in the realm of design studies and computer simulations. If it could be built, artificial gravity would help significantly with bone loss, muscle atrophy, cardiovascular deconditioning, and possibly the visual changes caused by fluid shift. But it would not solve the radiation problem, the fuel problem, the communication problem, or the psychological problem. It addresses one piece of a much larger puzzle. Radiation shielding concepts include several approaches, none of which are fully proven. Water walls, using the spacecraft's water supply as radiation shielding by arranging water tanks around the crew habitat, is a clever dual-use concept. Water is rich in hydrogen and moderately effective at absorbing cosmic rays, and you need to carry water anyway for drinking and life support. Placing water tanks between the crew and the exterior walls provides some additional shielding. The limitation is mass. Water is heavy, roughly 1 kilogram per liter, and the amount needed for meaningful radiation reduction adds thousands of kilograms to the spacecraft. Superconducting magnet systems that create an artificial magnetosphere around the spacecraft, deflecting charged particles before they reach the hull, have been studied theoretically. The physics is sound. Earth's natural magnetosphere works on exactly this principle. But generating a magnetic field strong enough to deflect the most energetic galactic cosmic rays would require enormous superconducting coils, powerful cooling systems to maintain superconductivity, and significant electrical power. The mass, complexity, and power requirements of such a system are daunting. Biological approaches are the most exotic, studying organisms like Deinococcus radiodurans, a bacterium that can survive radiation doses thousands of times higher than what would kill a human, or tardigrades, microscopic animals that survive extreme radiation, vacuum and temperature extremes, to understand the molecular mechanisms of their radiation resistance, and potentially apply those mechanisms to human biology. This is cutting-edge research, but very early stage. Genetically engineering human radiation resistance is a concept that is decades away from even laboratory feasibility, let alone application in space.